Good evening, Lamai. Okay, let's start the class for today. Today we are going to discuss about the electron gain energy, right? Under the period trends, we are going to discuss about the electron gain energy today, right? Okay, what is this means? The electron gain energy means? Yes, it is the ability of an atom. Actually, it is the energy change of an atom when it is gaining an electron, right? Or else we can say it is the energy change occurs when an electron is gained or when an electron is added to an gaseous atom, right? So that is the electron gain energy, right? So what is that? It's like if you have with a atom, gaseous atom, right? So if you add an electron to it to form the gaseous 1 minus ion, the electron gain energy is the energy change occurs or energy change involved with this process, right? That is the electron gain energy, right? That is the idea, right? Okay, so electron gain energy values are given in this table, right? So you can see some positive values as well as negative values are appearing, right? Some positive values as well as negative values are appearing with this table, right? This is in your notes, right? Okay, so we'll discuss what are these positive values, what are these negative values, and what are the trends we can observe with these numbers. Basically, what will happen going down a group, the basic trends going down a group, and the basic trends when going towards right as well, the period trends, right? So, and the special values. We'll discuss about those things. Right. First of all, I'll tell you what these positive and negative signs mean. What these positive and negative signs means in electron gain energy. Right? Okay, the idea is this. So, if when an electron is added, to an atom, let's say this is your atom, and this is your atom. You add in an electron. You add in an electron. When an electron is added to an atom, if the energy of the atom, if the energy of the atom, if the energy of the atom decreases, if the energy of the atom decreases when forming the negative species, right? If the energy of the atom species decreases, see, you are with higher energy, you are with a lower energy here. Then we say to decrease the energy like this, right? You need to release some energy, release some heat, right? We say such a process as exothermic process, such process as an exothermic process, and such situations we come up with negative electron gains. Negative electron gains, right? Negative means energy decreases. That negative values comes like this. When the delta E, the energy change, is negative, the energy change is negative. That means energy is decreasing. Energy is decreasing. You are starting with higher energy and you are ending up with a lower energy, right? In such a situation, we call the electron gain is coming up with a negative value. Electron gain is coming up with a negative value. Such things occur when you are release some heat when gaining an electron. When you are release some heat when gaining an electron. So such processes are also referred to as exothermic processes. Exothermic processes, right? As you release the heat, thermal energy is released. Exothermic, right? These things are called as, referred to as exothermic. Exothermic electron gains, which are denoted in negative signs. Those are negative things appearing in this table, right? What about the positive cases? What about the positive cases? Right? Positive cases. Positive cases occur when you gain an electron, when you're gaining an electron, if the energy of the particle increase, if the energy of the particle increases, so here at the start you have a lower energy and at the end you have a great energy. If the energy of the particle increases, that is what we refer to as a positive increasing, positive electron gain, positive value for electron gain, right? To happen such a situation, to come up with such a situation, definitely not only the electron, right? Not only the electron, but also you need to give some energy, some heat energy to those particles to increase its energy, right? To have a greater energy than the starting state, you have to supply some energy as well, right? So positive electron gains, also referred to as endothermic processes, endothermic electron gains, endothermic, right? So thermal energy, the heat is absorbed by the atoms to come up with positive electron gains. So that is what these negative and positive signs means in this electron gain numbers, right? So let's discuss when you see what are the instances you see the exothermic electron gains and what are the instances you will observe the endothermic or the positive electron gains. Let's discuss about those two, right? Okay. Almost all the atoms, right? Almost all the atoms other than three atoms, the beryllium, magnesium and nitrogen, other than these three atoms, right? The other atoms carry some negative values for the electron gain. These kind of processes, negative values for the electron gain, right? So only these three guys comes up with positive electron gains, endothermic values. Other than beryllium, magnesium, nitrogen, you clearly see all the values are negative electron gains, exothermic processes, right? So these three are referred to as endothermic processes. We'll discuss what are the patterns we would observe with these values first. With the negative values, what are the patterns we'll observe, we'll discuss. And we'll discuss why some guys prefer, right, exothermic processes, why some guys prefer endothermic processes as well, right? First thing, it is like this. So normally, we'll first discuss a bit about endothermic situations, right? Endothermic means, but actually, energy is low means you are much stable. Stability is high. Right? Low energy means you are much stable. Energy is low means ability to interact becomes smaller, so stability is high. So endothermic process means your stability will decrease. Your stability will decrease by the process. That is what happens with endothermic process. Stability decrease, right, as energy increases with endothermic processes. What about the exothermic processes? Normally, if you are to gain and stability, so here the stability is not that much, but here stability is gained. Lower energy means greater stability. Higher energy means lower stability. Right? Anyway, by the process, if you are to achieve much stability, that means if you are keen to do this process, if you become stable means when you are keen to do the process, when you are keen to gain an electron, normally such atoms comes up with a exothermic electron gain. When you are not keen to do the process, when you are not keen to do the process, when you are not keen to accept an electron, in such a situation, right, we will come up with an endothermic electron gain. That is the idea, right? We'll discuss first about these things, the exothermic situations. We'll discuss first about the exothermic, right? Exothermic situations, right? Exothermic electron gain situations. That is our first discussion, right? Exothermic situations. Right. Okay. We'll discuss. I'll discuss the exothermic situation here, right? Exothermic. Is a negative, right? Situations, right? We'll discuss that thing here. What are the patterns you would observe with the exothermic, the negative values, right? First thing you observe is, right, the first thing you observe with the exothermic electron gains first thing you observe is actually group 17s. See, group 17s are the ones which are with the greatest values for exothermic situations. You see, out of all these numbers, the group 17s carry the greatest negative values. This negative means heat is releasing. How much of heat? 328 kilojoules per mole. Right? These values are given in kilojoules per mole, right? Okay. These are energy values. Energy changes occur. 328 kilojoules per mole will be released. So greatest values, the greatest exothermic values, heat releasing values, are involved with group 17s. That is the first observation you see with these numbers. The second observation is next highest. Next highest comes up with group 16s. Group 16s. Let's discuss the reasonings behind those observations. Right? Behind those observations. Right. Okay. First thing. That's the first thing we need to grab from these trends. Right. First thing. The greatest. Or the highest. The greatest or the highest. Right. First electron gain. First electron gaining the first electron is with what? Group 17s. With group 17s. Group 17 elements. Right? Next highest are with group 16s. Right? Next highest values are with, right, group 16s. Right? That is the first thing you should know about the exothermic values of first electron gains, right? So when it comes to electron gain, right? Comes electron gain. Right? The highest value is for chlorine, you see, then for fluorine, then for bromine, then for iodine. Then comes the group 16s. Sulfur, oxygen, selenium, tellurium, all the others are less than that. All the other values are less than that. Releasing energies are less than the group 16s, right? Here you come up with the group 17s, here the group 16, right? Should always know about the greatest values. Even in ionization enthalpy and ionization energy, we had discussed about the minimum and maximum values. Like that, here also you should know the same. These are the maximum values with the electron gain, right? The maximum, right? Maximum values. First start with group 17s, then with group 16s. This is very clear. But this is very clear. Why is this? Why is this okay? Because group 17s are the most keen guys to gain an electron. Group 17 guys are the most keen atoms. Because group 17 represents the most keen atoms to gain an electron. Why is that? By gaining an electron, they can come up with the most stable noble gas configuration. By gaining an electron, the group 17s, as those are with 7 electrons at their valence shells, right? By gaining an electron, 1 electron, they can come up with the noble gas configuration, the most stable configuration. So that they are the ones gets the greatest stability. They are the ones which get the greatest stability by gaining an electron. The greatest stability is gain means energy is least there, so greatest heat will be released. Greatest heat or the energy releasement will occur when you achieve the greatest stability. Because with the greatest heat releasement, you will achieve the least energy at this state. That means you are gaining the greatest stability. That happens with when you are gaining the noble gas configuration by attracting an electron, gaining an electron. That is what happens with the group 17. That is one reason. That is one reason for group 17s to have the greatest exothermic values. Right? The one reason is, right, group 17s, right, achieve noble configuration by gaining the electron. The second reason for these guys to show the greatest ability or greatest first electron gain is those are the ones with the greatest effective nuclear charge. Those are the ones with the greatest effective nuclear charge. That means when going towards right, you know, the effective nuclear charge increases. No? So group 17 elements represent the right greatest effective nuclear charge other than the noble gases, right? We are not defining an electron gain values for noble gases because in when forming compounds, right, these guys are not involved, no? Right? Normally we are not defining values of those. So other than the noble gases, the group 17 guys are with the greatest effective charge, effective nuclear charge. Effective nuclear charge means the nuclear charge felt by the valence shell. The nuclear charge felt by a valence electron, or one can say the nuclear charge felt by the valence shell. So the electron is attracted to the valence shell. The electron is attracted to the valence shell. Electron is added to the valence shell. So that when that shell feels greater nuclear charge, when that shell feels greater positive charge, then electron will be easily attracted to that shell. So that is what happens with the group 17s, right? So this is another reason for group 17 guys to show the greatest first electron gain, right? Achieve noble gas configuration by adding an electron. And second thing, right, they are with the greatest first different charge, right? They are with the greatest, right, is a DFF, right? These are the two reasons for group 17s to show the right greatest first electron gain, right? Those are the most keen guys. Those are the most keen guys, right? Of gaining an electron, right? Then comes the group 16, right? Group 16. So those guys are with second greatest effective charge. So that is why they tends to attract the electrons, right, easily than the others, right? This is with the greatest effective charge, right, concerning non-metals, right? We are not considering the noble gases, right? Second greatest is a DFF. Is carried by the group 16s. That is why they are showing some considerable ability or considerable exothermic value to gain an electron, right? So this is the first thing, first idea you should know about the exothermic electron gains, right? Let's discuss all the ideas and then we can come up with the right note, right? We'll first discuss the ideas, right? Okay. Second thing, number 2. Okay, the second thing should know about the exothermic electron gains, right? The second thing should know. Before discussing about the second case, right? Let's try this now, Lama. So then there is a space given there, right? There's a space given there. See, it is said, right? So if the atom is keen, likes to gain an electron, energy is released, and such a process is called an exothermic process. That is called an exothermic process, right? This kind of a thing, right? Then they are saying, except beryllium, magnesium, nitrogen, all the other atoms have exothermic first electron gains. It is clear. Then it is said, group 17 and 16 are with atoms which are more keen to accept electrons, right? You can see here, right? So under that space, you can write that like this, right? The greatest or the highest first electron gains are with group 17 and group 17 elements. Next highest values are with this. So that space, right? For that space, you can write this one, right? The greatest or the highest first electron gain is with this thing, right? It is the first thing you should know, right now. Okay, right. So you can pause and write the stuff, right? Okay, then I'll come up with the second point. Second point you should know about these electron gain stuff, right? The second thing, right? These are the greatest values, right? Okay, let's see the next things. So next point I'm going to discuss about is actually what will happen going down a group. What will happen going down a group? It's normally you will see, right, when concerning third, fourth and fifth periods, right, gradually the first electron gain decreases going down. The magnitude decreases going down. The magnitude decreases going down. With this one also, magnitude decreases going down. Right? That is another trend we see. When concerning third, fourth and fifth periods, when concerning, not the second row, third, fourth and fifth periods, you clearly see the magnitude of those numbers will gradually decreases. Here and there some exceptions are there, but normally the number decreases going down. No? That is normal stuff, right? So we'll discuss why is that. We'll discuss why is that, right? So here also you see, right? When it comes third, fourth and fifth periods, the value decreases, right? Value decreases. You have some exception here, but normally third, fourth and fifth periods, right? The values are decreasing. Let's discuss the two things, why the values are decreasing like this and what happened to the fluorine, the second guy, right? Let's discuss about those two stuff. Right. Okay. Number 2, right? Number 2, the second consideration. about these electron gain trends, right? Second consideration. Second consideration is this. It is all about when going down. When going down, right? When, right? Going down a group. When going down a group, let's say, what will happen? When going down a group, right? Here we are concerning third, fourth, and fifth periods, right? What will happen, right? So basically, when going down, we see the atomic radius increases. Atomic radius increases. Atomic radius increases, right? When going down, atomic radius increases, right? Atomic radius increases, right? Going down, the atomic radius increases. When atomic radius increases, ability to gain an electron decreases, because this is your nucleus. Here the your nucleus, right, of your atom. So distance from the nucleus to the valence shell is far away here. Much distance is there. So attracting an electron becomes a bit harder for this one than this one. Attracting an electron easier here. So keenness of keenness of gaining an electron here is high and here is low. Right? When the atomic radius increases, ability to gain an electron decreases. Right? So ability to gain an electron decreases. So that we say the electron gain decreases. Electron gain energy decreases. The exothermic value decreases. So that is one trend we clearly see. Going down, see, group third, fourth, fifth periods, the electron gain values decreases. Clearly see, right now, electron gain values decreases. That is one trend to observe. Right? When going down a group concerning third, fourth, and fifth periods, right, is valid only for third, fourth, and fifth periods, not for two. Third, fourth, and fifth. You clearly see this trend. If you need some examples, you see, with the group 17, you see, the chlorine is at a greater value than the bromine, which is at a greater value than the iodine. Group 16, right, sulfur is with a greater value than selenium, which is with a greater value than selenium. For the group 15 as well, it is valid. Right? Normally it is a trend. Right? Phosphorus is with a greater value than arsenic, which is with a greater value than antimony. Sorry, antimony. Right? So this is the second thing we should know about the exothermic first electron gains. Exothermic first electron gains, right? Okay. Going down, right, the values decrease. Right now? Okay. So just quickly have a screen capture here and complete that note there. When going down a group, considering third, fourth, and fifth periods, the value decreases. This could be chlorine, bromine, iodine, sulfur, selenium, selenium, phosphorus, arsenic, bismuth, even sodium, potassium, rubidium. Right? Okay. Right now? is the second concern about the first electron gain. Alright, let's come up with the third important stuff with the electron gain. Right? Okay. See, even though the values are decreasing, going from third to fourth to fifth period, when considering the second and third rows, when considering second and third periods, that is not the case. Even though, right, fluorine is with a smaller size, still its electron gain is less than that of fluorines. Fluorine is with a exothermic value of 349, but fluorine is with a exothermic value of 328. The ability to gain an electron in fluorine is less than the chlorines, even though fluorine is smaller. So you would see some exception there. That same exception happens with all the periods. All the groups. When considering oxygen and sulfur, you see the same. Even oxygen is smaller than sulfur. One may think that the smaller guy will attract electrons easily and comes up with a greater electron gain than the larger one. But that is not happening here when considering second and third periods. The smaller guy is with a smaller number, not with a larger first electron gain. For all the stuff, this is valid. Even here, the largest exothermic value is with third row, even though it is large. The smaller guy gets a small value. That earlier rule violated here. The earlier rule, going down a group, the electron gain increases. That validates only for third, fourth and fifth periods. That is not valid for second and third periods. Here also, you clearly see the same. Here as well. Only instance that you see exception is here. Right. Discuss what is the reason behind that. Right? Okay, that is our third point to discuss. Right? Okay. The idea is this. Number 3. Right? Electron gain energy of, right, second row element is smaller than third row element. Even though radius of second row element is smaller than the radius of third row element. Right? Concerning a period. When concerning a group of elements. That is the third fact you should know about the exothermic electron gains. What is the reason here? I'll give you some examples. Right? When it comes to group 17, the fluorine is with a smaller value than the chlorines, which is with a greater radius. The oxygens value is smaller than that of sulfurs. The phosphorus value is smaller than that of nitrogen's value is smaller than that of phosphorus. The reason is, yes, we know becoming smaller is good for the first electron gain, but the reason is too much small is a problem. too much small is a problem, right? There is a saying ළමයි, there is a saying no, ඕනම දෙයක් ඕනමට වඩා ඕනෙම නැහැ. There is a saying like that, right? ඕනම දෙයක් ඕනට ඕනෙම නැහැ, right? So like that, okay? So becoming small is good for attracting an electron as your valence shell is more closer to your nucleus, but becoming too much small creates some problems. That is what happens with these too much small atoms with the second row. The too much small atoms with the second row. Third row here. Right? This is at the group 17. These are at the group 16. And these are the ones at the group 15. Right now? So the reason is what? The reason is, right? Reason is second row atom is too much small. That atom is too much small. So electronic repulsions have to overcome. Electronic repulsions have to overcome when adding an electron to it, right? When adding an electron to it. So it's like this, Lama. It's like this. So when you are small, right? When you are small, this concern your atom, fluorine with 7 electrons, then chlorine compared to chlorine, this larger with 7 electrons. So you see, much greater space distance between electrons with chlorine, but that is smaller with fluorine. So what will happen? What will happen? When you are add an electron, this distance, when you add an electron, this distance, right, becomes so smaller, so that electrons are very nearby to each other. So repulsions will occur. That is not good. But here, if you are add some electron here, right, some distance is maintained still because it's a large atom, not like in fluorine situation, as it's a large atom, right? So here electrons become more closer to each other, so that the electronic repulsions will occur. To overcome those repulsions, some of the energy release will be reabsorbed, right? To overcome electron repulsions, some of the energy released is reabsorbed. In the second row, with the second row element, right? That is why we say those guys are with a smaller first electron gain than the third row guys, right? That is the third important fact you should know about the negative values of first electron gain, right? The exothermic values, right? Electron gain energy of second row element is smaller than the third row element, even though the second row guy is small. Examples are given. So the reason is too much small becoming a problem. Electron repulsions have to be overcome after adding the electron, right? So some of the energy release will be reabsorbed. So releasing energy will be low. Releasing heat will be low compared to the third row element. So that is all you should know about the electron gain energies. right? No, that is the idea. It is about the exothermic electron gains, right? After that, so you can complete the note, right? After that, we'll come across the endothermic values, right? We'll come across the endothermic values, right? So with the space, so with the note, there's a space there. No? They are saying like at the next page, right? They are saying exceptional case, right? Even though second row atoms are smaller than third row atoms, still electron gain energy. Exothermic value for second row atom is less than that of third row atom, right? That is what it says. So this is because you can write like this: to overcome electron repulsions, some of the energy released is reabsorbed, right? Because second row atoms are too much small. So with these examples, you can write this stuff at that space, right now. Okay, that is all about the electron gain stuff, the exothermic values, right? Then we'll discuss about the endothermic situations, right? We'll come up with the endothermic situations, right? Okay, right. We'll come up with these guys, endothermic situations, right? Endothermic first electron gains. So I write the stuff again. So you had seen such three things are appearing, right? Endothermic, electron gains, right? Endothermic electron gains. This happens when, right? Adding an electron, when your energy increases. When your energy increases. Here you have lesser energy, here you have great energy. That means your stability decreases. Stability. Higher energy means lower stability. Lower energy means greater stability. When your stability decreases by adding an electron, right? Such processes are referred to as endothermic first electron gains. Endothermic first electron gains, right? So those happens, right? When you need to supply some energy to do the process, right? Endothermic. Let's discuss this situation. Which atoms tends to do this? Basically, when your atom is with a stable configuration, when your atom is with a stable configuration here and loses that configuration when gaining an electron, right? That is where you see this kind of an energy change. Here you have a stable configuration. By adding an electron, right, you loses that stable configuration. In such an occasion, you would observe this kind of positive values appearing with the first electron gain. Right? Let's see the examples. Only three are there. Only three are there. Only three are there with first electron gain as endothermic. See the examples. See the examples. Right? The examples. The beryllium, magnesium, and the nitrogen. The beryllium is with helium and 2s2 configuration. The magnesium is with neon and 3s2 configuration. You clearly see here these configurations are stable configuration. These configurations are stable configurations. And these are stable configuration. Stable configurations where S subshell is completely filled. completely filled. So these are stable configurations. When it comes to nitrogen, it is also carrying a stable configuration. The helium and 2s2 2p3 to 15. Right? See, your p subshell is completely exactly half filled. Stable configuration. Right? P subshell is exactly half filled. Right? So when you are with such stable configurations at the beginning, by adding an electron, as you loses that configuration, stable configuration, you are not keen to do that process. As you are becoming unstable, stability decreases by gaining that electron. Right? So only these guys are with such situation, right, here. So the beryllium, magnesium, nitrate. So those are the ones. Those are the only 3 atoms who are with endothermic values for the first electron gain, right? So you can clearly write these 3 stuff, right? You can write this picture as well as this one at the note, right? At the note, it is said, right, like this. Now they are saying if the atom is not keen, to gain an electron, energy has to be supplied. It has to be supplied to such a process, and as energy is absorbed by the reaction, such a process is called an endothermic process. Energy is absorbed, right? Heat energy is absorbed, right? As they are with stable electronic configurations, beryllium, magnesium, nitrogen do not like to gain an electron, so those have endothermic first electron gains. So you can come up with these, right? So stable configurations are there. So those are not keen to gain an electron, so electron gain comes up with a positive value, right now? Okay, that is the idea. So complete the note here. That is when you get the positive values, right? So out of these, what is your idea? Which is with a greater endothermic value, beryllium, magnesium, or nitrogen with a greater endothermic value. The more stable you are, the configuration is greatly stabilized at the beginning, then you are not preferring to gain an electron. So when it comes to endothermic values, right, that is greatest with the magnesium and beryllium than the nitrogen. These two configurations are more stable than this, right? More stable. So I'll write that thing as well if you need, right? So, right, so if you think of endothermic values, right, for nitrogen, right, is the smallest. The endothermic level of beryllium and magnesium are greatest because those are with more stable configuration, right? So magnesium and beryllium, right? Magnesium and beryllium, right? Comparing the two configurations, NS2 is more stable. One can say stability of NP3 is lesser than the stability of NS2. That is why this happens. Right? So this is how the endothermic values change. Right? Okay. That is all about the endothermic electron gains. You should know about the first electron gain energy changes. Right now? Okay, this is the idea. So complete the note. Right. After that, we'll discuss a bit more. We'll discuss a bit more about the second electron gains as well. Right? It is better to have that idea as well because those are questioned in your A-level papers, right? So let's discuss a bit, very small things about the second electron gain as well, right? Okay, second electron gain. Second electron gain. Right. Second electron gain. Right, the second electron gain. Second electron gain. Second electron gain is all about forming the 2 minus ion, forming the 2 minus ion, forming the 2 minus ion gaseous by adding an electron so that it should be added to the gaseous 1 minus. That is the Eg2. This is the Eg2. Right? Second electron gain means forming the gaseous 2 minus ion. Second electron gain means forming the 2 minus ion by adding an electron to gaseous 1 minus. So, like the ionization energy, that is the idea. The first ionization energy means producing the 1 plus gaseous atom by releasing an electron. Second ionization means producing the 2 plus gaseous atom by releasing an electron. Third ionization is producing the 3 plus gaseous atom by releasing an electron. Like that, the electron gains are also like that. First electron gain means by producing the minus 1, first electron gain minus 1 gaseous atom, gaseous ion by gaining an electron. Earlier it was releasing an electron, now gaining an electron for the electron gain. Second electron gain means producing the minus 2 gaseous ion by gaining an electron. Third electron gain means producing the minus 3 gaseous ion by gaining an electron. Nth electron gain means producing the minus n gaseous ion by releasing an, by absorbing an electron, by gaining an electron. That is the idea, right? So this is the second electron gain, right? Second electron gain, right? So when it comes to second electron gains, right? It is observed all the second electron gains are endothermic. All the second electron gains are, all the second electron gain energies are, or energy changes are referred to as endothermic. Endothermic. Endothermic means positive. Right? Let's discuss why. Let's discuss why. Even for oxygen, it is the same. Even for oxygen, it is same. Oxygen gas gaining the first electron gain is exothermic. This is exothermic. Negative. For the second electron gain, O gas gaining an electron to produce the O2 minus gas. That is endothermic, positive. Eg2 is positive. Let's discuss why. Let's discuss why. Why is that? The idea is this, right? Endothermic. So the simplest idea is when an atom refuses to gain an electron, not keen to gain an electron in such a situation, right? The value appears to be as a positive value, endothermic value. That is the idea. No? That is what happened with the noble gas. Sorry, that is what happened with the stable configurations as well. No? Beryllium, magnesium, nitrogen. In those have stable configurations, those refuse to gain an electron. Then the value will be as a positive value for the electron gain, endothermic. So for this situation, the second electron gain also such kind of thing appears. Why is that? Because you have an atom, gaseous species, which is negatively charged. So you are trying to add an electron which is also negatively charged. So this is a negative charged particle, the second electron gain. This is also negative charge particle. So these will repel from each other. This is hard to add that thing. Those things will repel from each other. Right? Negative particles will repel from each other. To overcome those repulsions, you have to supply energy. To overcome repulsions, right? You have to supply energy. See? No? So for that process, so I'll write it here. For that process, right, you need to supply energy. For E minus to convert to E2 minus, you have to supply energy as heat. So not only the electron but also the energy. That means energy here is low, energy here is high. That means process is actually positive. So energy increases by the process. That means process is positive. Means exothermic. Right? Ne? Okay. So all the second electron gains are exothermic. Second, third, fourth, all the second electron gains are exothermic because of these repulsions. Right now? So even for oxygen, even though it looks like it is achieving the noble gas configuration by attracting the second electron, still it is exothermic. So these repulsions are heavy. You know. So it is very hard to attract a negative particle to negative particle. So always repulsions occur between the similar charged particles, no? Same sign charged particles, right? So that is what happens. So second electron gains are always endothermic, positive values. Remember that. That will be also asked. So as a summary, one can say, when it comes to first electron gains, except beryllium, magnesium, and nitrogen, for all the other atoms, the first electron gains are exothermic, the negative values, right? For beryllium, magnesium, and nitrogen, the first electron gains are endothermic, positive values. When it comes to second electron gains, all the second electron gains are endothermic, the positive values, right? That is the summary, right? Okay, then at the end of the resource book, at the end section of the resource book with this topic, right, they are discussing about some other term, new term called as, right, electron affinity. Electron affinity. We'll discuss a bit about that term as well. Electron affinity, right? Electron affinity. What is this means? Electron affinity, right? Electron affinity. Right? Electron affinity. Right? Nothing much to know about the electron affinity. Actually, electron affinity means, let's say E. This is the only thing you should know, right? Electron affinity is actually the negative, the opposite of electron gain. That's it. So one can say EA is the minus EG, electron gain. This is the only thing much you should know about the electron affinity. Right? With this, you can answer any question coming from the electron affinity. Not that much of questions will be asked from the electron affinity, but this is the major stuff you should know. Right? The idea is this. Right? So if the electron gain as electron gain, equation is written like this. The first electron gain is written like this. If you're supposed to write the electron affinity, the EA is the EG. What you should know do is just write the opposite. That means here with A gas and E minus at the reactant side produces the A minus gas as a product, as the product. So for the electron affinity, it is just the opposite. From the A minus gas, you will produce A gas and the E minus. That is how we are how we should write the electron affinity equations. This electron gain, this electron affinity. That's it. All the positive values of the electron gain becomes negative, comes as negative values when it comes to electron affinity. All the negative values of electron gain comes as positive values at the electron affinity. That is regarding the numerical values. This is regarding the equation. That is the only thing you should know. These are the only stuff you should know about the electron affinity. It is just the opposite of the electron gain. The values are opposite means just the signs exchange with the numbers, and the equation also opposite means the reactants become products, products become reactants, right? Okay, that is all you should know about the electron gain theories, right? Okay, right. So we'll quickly have a break and then we'll start the next session. about the electronegativity, right?